Every single time you stream a movie, hop on a video call, or even just browse the web on your phone, you're tapping into a wireless channel. But have you ever stopped to think, is there a speed limit? I'm not talking about your data plan or the latest Wi-Fi standard. I mean a real hard limit, a fundamental speed limit baked into the laws of physics itself. Well, that's exactly what we're going to explore today. So, let's just put it out there. What is the absolute ultimate speed limit for sending stuff through the air? You might think with better and better tech, it's basically infinite, right? Well, not so fast. Turns out it's not infinite at all. Just like a sports car has a top speed it just can't break, every single communication channel has a maximum data rate. And this limit, it's not arbitrary. It's governed by some really elegant fundamental principles of something called information theory. And today, we're going to unpack it all, piece by piece. All right, so here's the game plan for our journey today. First, we'll get a handle on what this ultimate data rate actually is. Then we'll start simple, looking at an ideal channel. Think of it as a perfect pipe. From there, we'll get a reality check and dive into the messy world of fading channels. The fun part? We'll uncover the best way to deal with that mess, a strategy called water filling. After that, we'll see how this applies to an even more complex pipe. And we'll wrap it all up by talking about why any of this channel capacity stuff actually matters. Okay, so this ultimate speed limit, it actually has a name. It's called channel capacity. And this whole idea comes from an absolute giant in the field, Claude Shannon, who's pretty much the father of information theory. What Shannon proved, and this is mind-blowing, is that for any communication channel, there's a specific maximum rate where you can send information with practically zero errors. If you try to push data faster than that limit, well, you're guaranteed to get errors. It's a mess. But if you stay at or below that magic number, perfect communication is, at least in theory, possible. It's like a cosmic speed limit for data. Now, this can all sound a bit abstract, I get it. So to make it super intuitive, we're going to use an analogy that we'll stick with for this whole explainer. It's simple, but it's really powerful. Just imagine that all the data you want to send, your movie, your video call, is water, and the wireless channel it's traveling through, that's a pipe. So what's the channel capacity? Easy. It's the maximum amount of water you can possibly shove through that pipe at any given time. That's it. Keep this water and pipe idea in your head because it's going to be our guide as we start to tackle the more complicated stuff. All right, let's start simple. Let's imagine a perfect world, a theoretical paradise for communication. We're talking about the ideal channel. In our analogy, this is like a brand new, perfectly smooth, rigid pipe. Its diameter never changes, it's totally fixed, and we know exactly how big it is. It's the most straightforward case you could imagine. But even in this perfect world, there's one pesky little problem that we just can't get rid of. And that challenge has a fancy name. Additive white Gaussian noise. Let's just call it AWGN for short. So what is it? Honestly, just think of it as the background static of the universe. It's always there. We call it additive because it adds on top of our signal, messing it up a bit. And it's white because it's like white light. It hits all frequencies pretty much equally. So what does this mean for our perfect pipe? Well, the AWGN is like a constant, super predictable, low-level leak. No matter how perfectly built our pipe is, a tiny bit of water is always going to be seeping out. It's just a fact of life. Okay, so let's recap where we are in our perfect world. We've got a pipe with a fixed, unchanging diameter. That's our channel. And we've got a constant, predictable little leak. That's our noise. In this scenario, figuring out the channel capacity is pretty straightforward. The max water flow is just limited by how big the pipe is and how much it leaks. It's a nice, simple, fixed number. But you and I both know the real world is never, ever this neat and tidy. All right, it's time to leave our perfect theoretical world behind and step into reality. And in the real world of wireless, there's this one huge thing that changes everything. It's called fading. This, right here, is what makes wireless so much harder than just sending data down a cable. And for our analogy, it means our perfect, rigid pipe, well, it's about to get a whole lot weirder and a whole lot less predictable. So what exactly is fading? In a nutshell, it's the wild, rapid fluctuation in how strong a signal is. See, a wireless signal doesn't just go from point A to point B in a nice clean line. No way. It bounces off of everything. Buildings, trees, people, you name it. So what your phone gets isn't one signal, but a whole bunch of copies that all took different paths and arrive at slightly different times. Sometimes they add up and make the signal stronger, but other times they cancel each other out, making it weaker. It's a chaotic mess. So what does this do to our pipe? Well, you can throw that rigid pipe idea right out the window. Now we've got a flexible, rubbery hose that's constantly and unpredictably widening and then narrowing from one moment to the next. This brings us to a really, really crucial idea. It's called channel side information, or CSI for short, and it all boils down to a simple question. Who knows what the channel is doing right now? Who knows how wide our pipe is at this exact moment? Let's look at two scenarios. On the left, let's say only the receiver knows. The transmitter is just sending data blind. This is like shouting into a howling storm and just hoping the person on the other side hears you. The receiver can only tell you after the fact that they missed what you said. When that happens, when the data doesn't get through, we call it an outage. It's super inefficient. But now look at the right. This is the game changer. Here, the transmitter also has that information. Both the sender and the receiver know the pipe size in real time. Now, the transmitter can be smart. It can adapt its strategy on the fly. It's the difference between shouting blindly into a storm and waiting for a quiet moment to speak clearly. It's being proactive instead of just reactive. So this sets up the central puzzle for us, right? If our pipe is constantly squishing and stretching, but, and this is the key, we know its exact size from moment to moment, what's the smartest thing to do? How should we adapt our water flow? Should we just try to push water through at a constant rate and hope for the best? Or is there a more intelligent, adaptive strategy that will get us the most water through over the long run? Well, it turns out there is an answer. And it's not just a good idea, it's the mathematically perfect solution. It's an incredibly elegant and powerful strategy called water filling. When you have that full channel side information at the transmitter, this is the absolute best thing you can do to send data over a fading channel. And honestly, it's one of the most beautiful and intuitive concepts in all of communication theory. So what is this water filling thing? At its core, it's all about being smart with your power. It's an adaptive power allocation strategy. The basic idea is just pure common sense. When the channel conditions are great, when the pipe is wide open, you seize the opportunity and pump more power in. But when the channel is bad and the pipe is narrow, you back off. You use less power and save it for when conditions get better. It's just formalizing that very simple idea we talked about earlier. Don't waste your energy shouting into a hurricane. Let's really break this down using our pipe analogy. So, step 1, the channel is good. The pipe is wide open. What do? We crank up the pressure. We use more power to send data at a much higher rate. Step 2, the channel gets bad. The pipe suddenly narrows. The smart move? We ease off the pressure. We use less power and send data at a slower, more careful rate. And now for the most surprising and crucial part. What if the channel becomes terrible? Like the pipe is pinched almost completely shut. The optimal strategy, the mathematically best thing to do, is to use zero power. Absolutely none. You literally turn off the tap and just wait for the pipe to open up again. This is exactly why your Netflix stream might suddenly pause and buffer when you walk into another room. Your phone or router is making a calculated decision that the pipe is just too narrow right now, and it's better to wait than to waste energy trying to force data through, only for it to get lost. And this idea is summed up perfectly by Dr. Andrea Goldsmith, whose textbook is the foundation for this whole explainer. She says, the intuition behind water filling is to take advantage of good channel conditions. That's really all it is. It's about being opportunistic. It's about being smart. By strategically pouring our limited power into the moments when the channel is at its best, we squeeze out the absolute maximum amount of data over time. Okay, so we've got a pretty good handle on how to deal with a channel that changes over time. But reality is about to throw us another curveball. There's another layer of complexity we have to deal with. So far, we've been assuming our pipe has one single diameter, even if it's changing. But what happens if the channel acts differently across different frequencies at the same time? This is what we call a frequency-selective channel. To get our heads around this, we need to upgrade our analogy. So imagine our one big, flexible pipe now splits into a whole bunch of smaller, parallel pipes, all running side by side. Each one of these little pipes represents a different slice of frequency, a subchannel. And here's the crazy part. Each one of these little pipes has its own independently changing diameter. So at any given instant, you could have one little pipe that's wide open, another that's kind of narrow, and a third that's totally pinched shut. This is exactly what happens in the real world. A Wi-Fi signal might be fantastic at one frequency, but absolutely terrible at another, all at the very same time. So how do we handle this? What's the optimal strategy now? Well, it's beautiful, really. We just use the exact same water-filling logic, but instead of applying it over time, we apply it across these different frequency pipes. Let's look at this example here. Imagine we've got a certain total amount of power to use, and we can split it between these 3 subchannels. The water filling algorithm takes one look at the situation. It sees subchannel 3 has amazing quality, that's a wide open pipe, so it pours the most power into that one. Subchannel 2 is pretty good, so it gets a decent amount of power, but subchannel 1 is weak, that pipe is narrow, so it only gets a little trickle of power. And you can bet if there was a fourth subchannel that was just awful, it would get absolutely zero power. We wouldn't waste a drop. And this right here is the fundamental principle behind a technology called OFDM, which is the engine that drives modern 4G, 5G, and Wi-Fi. Wow. Okay. So we've come a long way, haven't we? We went from one simple, perfect pipe to this complex system of parallel pipes that are all changing in both time and frequency. So now, let's bring it all back down to earth. Let's connect all this theory to the actual gadgets in our hands and the networks that make our modern world tick. Why does any of this, channel capacity, water filling, why does it actually matter? Okay, let's boil it all down. Here are the most important things to remember. First, every single channel has a finite, unbreakable speed limit. We call it capacity. Second, the real world isn't a perfect pipe. This thing called fading makes it totally unpredictable. Third, the absolute key to getting great performance is knowing what the channel's doing at any given moment. And fourth, the best strategy isn't to brute force it, it's to adapt. That's what water filling does. It allocates our resources intelligently. And this last point is huge. This isn't just some abstract theory from a textbook. This principle is the literal foundation of the tech we use every single day. Modern Wi-Fi, 4G, and 5G all rely on these ideas to give us the speeds we expect. And so all of this leaves us with a really big, thought-provoking question for the future. We now understand that there is an ultimate speed limit, a hard ceiling set by physics. So as our hunger for wireless data just explodes, for higher quality streaming, for virtual reality, for a world full of connected devices, how close are we actually getting to that ceiling? Are we pushing up against these fundamental physical limits? And maybe more importantly, what happens when we finally hit that wall? What kind of new breakthroughs will we need then? Hey, if you found this deep dive helpful and you enjoy getting into the nitty-gritty of how our world works, do me a favor and subscribe to the channel and give this a like. And I'd love to hear from you. If you have any questions or if there are other topics you're curious about and want to see explained, just drop them in the comments below. Thanks so much for joining me.